Okay, so this is 1980 mechanics question 3. Okay, so the diagram shows a billiard ball of mass m, radius r. It's being pushed. It's initially pure translational, then it's rolling with slipping, and then it's rolling without slipping, as seen by the diagram. Okay, so we have velocity v naught. So we have v naught. We have inertia equals 2/5 mr squared. That's inertia of a sphere. And then we also have mu k, which is the friction between the ground and the ball. Okay, so A. We're supposed to determine an expression for linear velocity v at the center of the ball. So center of mass of the ball as a function of time while it is rolling with slipping. So with slipping means that there is a frictional force applied to it. So that means, well, from kinematics we have that v equals v naught plus at. A is negative because it's going against velocity, so v equals v naught minus at. We are supposed to find what A is because, well, right now it's not given in terms of what we're given. So this acceleration is found by Newton's second law. Force equals ma, which in this case is equal to the frictional force applied, which is indeed mu k times the normal force. The normal force is the weight, which is mu k m g. We're given m. So setting these equal, we get A is equal to mu k mg over m. The m's cancel out, so we have mu k times gravity. Plug that in, simple as that. V equals v naught minus mu k g times time. That is v. That's a v, by the way. It's a v. Okay, so B. Do it over here. We're asked to develop an expression for angular velocity, omega. Okay, so kinematics, angular kinematics actually. Omega equals omega naught plus alpha t. In this case, there was no initial omega naught because it was initially pure translational. So this is 0. Get omega equals alpha t. And we have to find alpha. One way to do that, torque. Torque equals I alpha. You guys need to know this equation. So torque also equals the radius times the force. Well, this is perpendicular force, and we can assume that it's perpendicular because it is. So RF equals I alpha. R is big R. Force is the frictional force, which is mu k mg. I is 2/5 mr squared, and alpha is what we need to find. So cancel out the m's. Cancel out one of the r. So mu k g is equal to 2/5 r times alpha. That means alpha, if you move everything to the side, is 5/2 mu k g over r. Hope you guys can read that. Okay, so that means we found alpha. Plug it in. We have omega is equal to 5/2 mu k g over r times t. That's omega. Okay, so we are on to part C. I'll erase this. Part C says, let's see. So, part C says, determine the time at which the ball begins to roll without slipping. Okay, so for this one you have to know that slipping stops when tangential velocity is equal to center of mass velocity. And we know tangential velocity is equal to omega r. And this velocity is equal to v naught minus mu k gt as found in part A. So, set these equal. We have omega r is equal to v naught minus mu k gt. Now omega, is what we found in the previous problem, is 5/2 mu k g over r times t. So, plugging that in, we get 5/2 mu k g over r t times r. These r's cancel out. This equals v naught minus mu k g t. We want to find t here. We want to find the time at which the slipping stops. So, move everything to one side. This is 2/2 plus 5/2. This is 7/2 mu k g t equals v naught. So, the time at which slipping stops is v naught, 2/7 v naught over mu k g. That's time. Okay, so last part D. I'll erase this for room. Okay, so part D asks, when the ball is struck, it acquires an angular momentum about the fixed point P on the surface, right there. During the subsequent motion, the angular momentum about point P remains constant despite the frictional force. Okay, explain why this is so. Okay, so frictional force is applied through the point P. So that means that net torque around point P due to all forces is 0. Because net torque is 0, that means angular acceleration is 0. So the initial angular momentum will not change. So angular momentum stays constant. This can also be shown by the equation omega equals omega naught plus at. You know that angular momentum is inertia times the omega, right? But since angular acceleration is 0, this is gone. So omega stays as its initial omega, so L is conserved.